chemistry, and we're in section 3, and we're going to talk about voltaic cells. So voltaic cells, what are these voltaic cells? Well, the definition here, so it really is telling how voltaic cells are how spontaneous redox reactions can produce an electric current. So, and we know that there are a lot. You are undoubtedly familiar with the various types of batteries used to power, like batteries in flashlights and watches and in portable electronic devices. And so these are all voltaic cells. So voltaic cells, considered another word, batteries. Voltaic cells are devices that convert the chemical potential energy of spontaneous redox chemical reactions, which we've been talking about, into electric energy. So that's kind of important that you know that definition of what a voltaic cell is. Now they want us to construct a voltaic cell. And you'll probably have an experiment on this if you want to really look up how to do this. But here it's just going to be described in some pictures. But we're going to go over this voltaic cell. So let's go along. Here's a picture of the reaction between zinc metal and copper in this voltaic cell. Well, the construction of voltaic cells are these spontaneous redox reactions, and where metals are giving up electrons very easily to form cations. And the metals at the top of the activity series, which we found before, there's some metals that are very strong reducing agents. They're very active metals. And we had this in the last chapter, on chapter 15, section 3. You can go back to that and find out which metals are more active than others, because they're really wanting to bring themselves into a reactive situation with another, because they need to accept electrons or get rid of electrons, right? So this makes them very active. When two different metals are involved in a redox reaction, the metal higher in activity, the more active metal, will be oxidized and give up electrons, reducing the cations of the less active metal. So now we're not just going to go by which ones are positive and which ones are negative, but which ones are more negative, because the more negative actually will take over the power and oxidize and give up electrons and become the active metal. So if you have two different metals, so this is what's going to happen in the voltaic cells. Voltaic cells, you're going to have two different metals. In fact, it says in italics here, when two different metals are involved in a redox reaction, the metal higher in activity will be oxidized and give up electrons, reducing the cation, exactly what I said with the less active metal. So this is important right here. So we need to, we need to know which ones are more active. Remember we had that chart which told us that those that were more active than hydrogen, and that was on that chart. So on that chart, that table, we can see that zinc is more active than copper. So if you take a strip of copper and a strip of zinc. First of all, let me just go over this whole situation. Just look at what's happening right here, because this is a zinc and copper here. The copper and the zinc, the copper sulfate solution here. So what we're going to have a reaction between, first of all, this one has a zinc strip. So what's happened if we put a zinc strip in a solution of copper? We put this in here. What happens with the zinc strip in a solution of copper? Well, this is what happens. The solution loses color as the copper ions are replaced by the zinc ions. So, but if you do the opposite, if you took a copper strip and put that copper strip into a zinc solution, which they have done before, they took a copper strip and put it in the zinc, and you'd think, oh, this would react too, but it doesn't react. The copper zinc within the zinc, or the copper strip in a zinc solution, the zinc solution being zinc sulfate, put it in zinc sulfate, there's no reaction at all. So if you took a copper strip and put it in to a zinc solution, nothing would happen, because the copper is too weak to overcome the zinc. But in this situation, we took a zinc strip, which is the more active metal, and we put it into a copper sulfate. And you can see what happens right away. The zinc is oxidized right away, and you can see the zinc is dissolved into the solution, causing the copper solution to lose its color of copper as the copper is reduced. And the copper metal basically crumbles back, is crumbling back. The copper metal is crumbling back and coating the zinc. See how it's coating the zinc? We talked about that coating in the last section. So it's coating the zinc strip. So this blue copper solution loses its color, and then the zinc has copper on it. This is what happens when you put a zinc strip, because the zinc is stronger, into the copper solution. Now try opposite with the copper, you'll get nothing at all, because the copper is not strong enough to overcome the zinc solution. So, and what is basically, here we have the reaction going on, the oxidation right here. Here's the equations. You have the zinc. Here it's turning into the ions. The zinc wants to actually come out to unite, so it ends up, the zinc is turning into 2 positive ions with 2 electrons freeing themselves. That's oxidation. Oxidation, and then on to reduction. The copper is basically taking these 2 electrons into forming copper. So here we have the reduction. The reduction of copper ions, the copper ions in here, are wanting to basically turn back to copper, which they will there. So we can combine these two together. You just basically have the zinc here and the copper down here. Electrons are on this side and the electrons are on this side, so we can get rid of that. And on this side, we have the zinc and we have the copper. So this is going to be our net equation. When we take out anything that's on both sides, that's going to stay as the same on both sides as these electrons are, and that's what we have. The sulfur, sulfate ions here are in the solution, and they are just spectator ions. They have to be there though, but they're spectators, but they do not participate directly in the reaction at all. So, because you're going to have copper sulfate to make the copper in the water. So you have copper sulfate in the water. The sulfate ions are just spectators, but they actually are catalysts too. So that situation. So now we're talking about these Voltaic cells. This is going to, well, what happens in these Voltaic cells? This is the process that we're talking about, constructing a Voltaic cell, and we're going to make one, right? So let's go on to the Voltaic cells here. So separating, it says separating half reactions here. And so far the reactions are of little use. Okay, this is cool. Good colors and everything. Yeah. And there's some heat produced, but so what? But no useful energy is produced. But if we want batteries, how are we going to do this? So it is possible now to separate by rearranging the cell in a certain way to produce these electric currents to flow through. And so this is by dividing the beaker into 2 compartments. Like this we wouldn't do with this. It might be good for copper plating, but that's about it, right? And so now we're going to show how a battery works, the power of a battery. By rearranging the cell the way we like, we can actually we can control the amount of energy that's going through with the electrons in the midst of this. So the beaker is divided into 2 compartments by a porous divider, and one side contains zinc immersed in a solution of zinc sulfate, in fact, and the other side contains copper. The same type of procedure here. Now we're going to put in a battery. So let's see how it goes. Here we have the pictures, so you can go along with the pictures. So initially, there's like little reaction occurs, or no reaction. Then there's a small negative charge that builds up. And then the charges, are not equal. The zinc strip is more negative, of course, than the copper. And so the voltmeter for the zinc is going to be higher more negative or less positive, however you want to say it. And then it's connected to the strip with a wire. And that's the deal, connecting with the wire. So here we have in this simple Voltaic cell, no redox reaction is occurring. Nothing is happening as long as the zinc and copper strips are kept separate. So they have basically a separation here. So it looks like it's almost two beakers, but it's one beaker with a separation. So here's the copper sulfate is, going to be floating around, and in the midst of this, the copper sulfate in the solution. Here's the porous divider. It's cardboard here, cardboard. So it's not like totally going to separate. Some electrolytes are, especially the sulfate, the sulfur is going to go back and forth. So here we have this divider, and on this side we have the zinc sulfate solution. So it's a different. Still, remember, the sulfates on both sides, zinc sulfate and copper sulfate on this side. And we have this solution here with the zinc strip. Okay, this is our battery here. And this is this simple voltaic cell right here. And we can see as the zinc and copper strips are kept separate. Okay, that's first, keep them separate. And so B, at equilibrium, so far nothing's really happening, that at equilibrium each strip has a slight negative charge. However, zinc is slightly more negative than copper. So we have the zinc side a little bit more negative than copper because it's a more active metal than copper, like we said before. So here's the situation. So we measure each side, and each side has a voltage a little bit, but it's slight. But then what happens in C here, what we do here, this looks like a huge thing. So when a huge reaction. So when we separated the zinc and copper strips and then we connect them now, a redox reaction occurs. But oxidation and reduction occur at separate locations. And an electric current flows through the wire from one site of oxidation to the other site. Isn't it? If you have all these batteries and you think, well, what in the world? You try to open a battery and you get all this, all of this metal and this sulfuric acid and everything coming out, which it's involved in. And you wonder how we get electric current. Well, here's the deal. So the reactions, a steady current starts flowing here. So the reactions are starting to happen because we ended up connecting these two with this wire. So as we connect it, this steady current starts flowing through the connection. So because, the zinc, being the more reactive, is going to push out the electrons. I say pushing out the electrons, it's going to go over here to here because the electrons want to get over to this copper side now. So the electric current flows through the wire from this side through the side of oxidation on this side and to the side of reduction on this side. That is our battery. The sulfuric acid in the midst, the sulfate, is diffused from right to left to keep the charges on both sides balanced. So in the midst of this, you see the sulfur, the sulfate oxygen, the acid here, is basically able to go through this cardboard back and forth to keep it all going. Otherwise, it would stop. But since this is happening here, which it's a spectator, really, it's not going to be involved in the reaction itself, but it's keeping the aqueous solution going. And so in that way, you're going to have this current going through, and that's our battery. So how cool is that? The divider must prevent the solutions from mixing, because if the copper all of a sudden just contacts the zinc strip, then right away it would be reduced and it would just jump on like this. So if you took this cardboard out, because right here it's preventing the copper from going, it's preventing the zinc from going here. That's why the electrons are shooting out here. It's preventing here. Although the acid is on both sides going through there, it's semi-impermeable to semi-permeable to the acid and not to the metals. Again, up here, it would happen like this. So if we took it out, bingo, bam, this would happen, right away. But instead, since we have this, we're controlling this. I mean, who ever thought of this? And suddenly the current's going out through. So that's a simple voltaic cell. And these half reactions are carried out as you go through in separate areas. In the lab, you'll see they'll put a different container salt bridge in the midst of this. But this is what we have for a simple voltaic cell. In fact, here's the voltaic cell as a source of energy. So now it's not, so useless to us. Now we can take our batteries, and as we hook up the electrodes to the sides, and these are electrochemical inside of these batteries, as the batteries are hooked up, and as we hook them up, all of a sudden we have this electron current going from the zinc, lighten up the light bulb because there's electrons are traveling, electricity is traveling, going through here and lighten up the light bulb, and as it goes around back to the other side. And then again, it keeps going till the batteries are used up, And so also in the midst of this, you could have what's called the salt bridge. So if this, as it's using up, this is a simple battery, but now instead of putting this cardboard here, which is not the best thing inside a battery, right? Or, something that's more, they put in a salt bridge, and this salt bridge is takes the same place as that divider there. So that salt bridge. In fact, here it says, in the laboratory, half reactions are often carried out in separate beakers. And this arrangement, called a salt bridge, is a tube filled with a non-reactive electrolyte that takes the place of the porous divider in equalizing the charges. And this arrangement allows less mixing of the solutions and prolongs the life of the cell. So they put the salt bridge instead so that, basically cardboard's going to melt away, right? Pretty easily. So they put the salt bridge in and put them in separate beakers. And this way it works too. It's so amazing because here you have the salt bridge, which the sulfuric acid is just, in both the same, can basically, can travel on the salt bridges to keep equilibrium, but the zinc and the copper are in this way prevented. So they want to do this. They want to go up this bridge, but they can't do it, just like they can't get through here. And so then the electronic current, or the electricity, is you hook these two electrodes up, move to the right, just like you do in your car battery. You're hooking the electrode, and this electron current goes through to the other side, because the zinc wants so badly for the electrons to get over to this copper. Can you believe this? So how they ever thought of this, but this is, God putting things together. So this is a Voltaic cell using a salt bridge. So here is our equation. So again, the oxidation, the zinc strip is going to be zinc. It wants to get rid of those electrons. It wants to get rid of electricity. And so in doing that, because it wants to be normal. Remember I said zinc really wants to be normal, but it has extra electrons extra, so basically as a positive, it's in the electrons given off here. So in the copper, of course, wants to. So what happens here? This is kind of weird because the zinc actually, because it's more negative, it wants to go to the less negative copper, although they're both in the negative. So this is kind of a weird deal, but that's the way it happens. The more negative wants to go to the less negative, right? And so here we have the situation here, both in doing with electrons, with the reduction, the oxidation, and the reduction. So let's go back with corrosion. We're going to talk about corrosion. I'll do that at the end. Measuring electrode potentials now. So both, it says in the simple voltaic cell, Both electrodes developed a negative charge when you immerse them in their solutions. So they're both negative. However, the zinc electrode developed a stronger negative charge stronger negative than the copper electrode because zinc is a more active metal. As a result, a voltage existed between those two electrodes, amounting to a potential difference of 1.1 volt. Their difference is 1.1 volt. So we can state in general that the more active substance, the stronger the negative charge that develops when the substance is at equilibrium with an electrolyte solution, is that metal is more active. And so that's when they set up, okay, we need to have some kind of activity table of measuring this. Okay, first of all, let's look at this, measuring standard electrode potentials. So now they have, look how elaborate our battery cell's getting. So now we have the standard hydrogen electrode. So they're going to put in a standard, and they put in this hydrogen electrode to measure. And so here they're using the measure device to measure the voltage, to see how the voltage in comparison to hydrogen. And hydrogen's pretty moderate. It's like the middle of the road measurement. So they're going to measure that, and they put the hydrogen gas through here so that they can measure the voltage, right? And so, and this is to be tested. Basically, they're testing this. Here we have, you can test, they're testing this side, and of course, here here they're using this to test this side. So this is how they use to find out, what the standard hydrogen electrode and what is the voltage and such. What is the voltage for the zinc at rest, and what is the voltage of the copper, so they can find out which one is more active than another, and then they can find out what kind of metals they can use in these cells. So now we're going to talk about this standard electrode potentials. So chemists often express the tendency of a substance to form a stronger or weaker charge when placed in an electrolyte as the substance standard electrode potential. And this potential is like an E with a little degree mark there. So E degrees. So for convenience, hydrogen, which is a moderately active substance, will be assigned the standard electrode potential of the 0 volt. So using hydrogen. So this electrode material that is more active than hydrogen is going to be considered more easily oxidized, and they'll have a negative electrode. And the electrodes that are less active than the hydrogen will have positive electrode potentials. So here is the standard right here. So we're going to put down hydrogen as sea level. If our hydrogen is sea level, then anything above the standards, or below, we'll consider compared to that sea level, right? And that's kind of what we do now. We compare mountains, how high a mountain is to a sea level, which is kind of, you could compare it to anything. So you always have to have a comparison, is all they're saying. So, but now we're going to take hydrogen, and it's kind of moderate. Anything above that reacts above is going to be positive, and what's going to be below is going to be negative. But the ones below are going to be more active because they're more negative. So it's actually the ones down here are boiling up to get out, right? Nitrogen, cadmium, and zinc down here. And then, of course, we have copper and gold and silver that are positive compared to hydrogen. So they're just comparing everything to hydrogen in this standardness of this. So going on here, the standard electrode potentials of different substances are measured by the means of a special Voltaic cell containing hydrogen to be put in and tested. And because this hydrogen is a gas, it must be bubbled across the surface. So it's kind of weird, bubbled across, and the half cell containing the hydrogen apparatus is called, the standard hydrogen electrode is called She. Standard hydrogen electron. They always have these names, the She electron. So we're putting the She in here, which is the standard hydrogen, and we're bubbling the gas through, bubble, 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 and then we can get this to the measurement of what the voltage is going to be for zinc and for copper later. We're doing both. This is the She standard. And that's how they do it. Bubble it through. And they're going to measure this standard again in this E. This E with a little degree, the degree E. Thus, 0.76 volts, is for zinc. Zinc ion has 0.76 volts less tendency to be reduced than the hydrogen ion. So its standard would be what? It's going to be, here it is, zinc is going to be a negative 0.76, and then you're going to have zinc being negative 0.76, and then you'll have copper is going to be up here, is going to be a plus 0.34 volts. So this is, we're measuring by volts. So, and that's going to be positive. So, and these are going to be the E values, the E degree, or measured by the She and E. And here, this is a standard reduction potential for this here. And so we're going to have, these are all the values of the standard reduction potentials with the hydrogen, right? So here we have hydrogens in the middle. Here's hydrogen, electrons are here. And we have weak oxidizing above here, and then the increasing in strength. And then we have strong reducing. Of course, the oxidizing and reducing are opposite. And so we can look at each one. So if we take zinc here, we have zinc, and we have oxidation is the two electrons there that going on to electropotential is negative 0.76. Then if we go down to copper, what we had before, copper here, and in the midst of copper, we're going to have this, and we'll end up having this strength towards hydrogen, 0.15, or here's copper 2 is 0.34, which we were looking at. So it depends on what you can find out. This is just finding out their standard, how active they are, and they measure it by using the hydrogen being middle of the road and how they compare, because hydrogen would be 0. Things below are things that are above, depending on which way you're going. This is the increasing strength for the reducing agencies, and this is the increasing strength for the oxidizing. So as you go, strong reducing agents are going to be the real negative ones. They're going to be strong reducing agents, and the ones that are strong oxidating then the opposite. So I hope you understood this a little bit. The She standard is, just remember that, is that hydrogen, how to measure how active they are. And so here is calculating the cell voltage here. So calculating the cell voltage. Once we know the standard of reduction potential in each, and this electrode in our Voltaic cell, we can predict now, why do we need to know this? Because then we can predict what metals we want to use, right? And in our batteries. And they use a variety of different kind of metals in batteries, that is for sure. And so we can predict the overall voltage of the cell, how much electricity is going to fly through that cell by exactly the two different metals and their potentials. So now we can say, okay, in a battery, do you want a strong battery? Do you want a weak battery? Is this battery going to last a long time? We can know all these potentials, the potential by the standard reduction potential, and which one is more active than another. So, in any Voltaic cell, the electrode that's more negative potential will be going through oxidation. So in oxidation, not reduction, so you're going to have to, the difference is when you have an equation, you're going to have to change the one that's more negative is going to be so more negative that it's going to reverse its sign and turn into a positive sign. That's the tricky part of this. So here we have here, it says, let me repeat that. In any voltaic cell, the electrode with the more negative reduction potential will be undergoing oxidation, not reduction. Thus, the sign of the reduction potential E will be reversed for that substance. For example, let us return to the zinc copper cell. Okay, since zinc has a more negative than copper, we know it will undergo oxidation. So here we have, after this is done, we can find the net charge. So basically we have zinc here, and we have zinc. This is just normally what we had before. We have the anode and the cathode and the net. So this is what we had before. Zinc, the electrons coming on one side, going on to the other, and this is our whole formula, right? So now we're going to put in the zinc, the E, which again, what is the E? Standard reduction potential that have to do with hydrogen. So we put in the E, and that's plus, oh, I thought it was negative 76. We had to reduce it because it's going to act differently, oppositely actually. So it was a negative 76. Well, we're going to change it to positive 76 because now in the midst it has changed from what it's doing from oxidation to from reduction to oxidation. So here we have, and so now we have the E with the voltage sign. This is the same with copper, and so now we add them together and we get a lot of volts because of zinc changing and because it's more active or less negative, really getting volatile, then it changes, and then we have E, we can measure it as 1.10 volts. A voltage difference of 1.1 volts will exist between zinc and copper strips. So let's stop there, and I'm going to go on to this last part in the next video.